And now I'm going to leave the floor to our guest speaker, Ming-Chang Liu, who a lot of you know already. Ming-Chang is a cosmochemist and a secondary ion mass spectrometry specialist at Lawrence Livermore National Laboratory in the USA. So Ming-Chang, I'll let you share your screen.
Thank you. Let's see. All right, so share, and I need to make sure. Okay, there we go. Okay, great. Thank you very much, Celine, for the introduction, and good morning, good afternoon, and good evening where you are. My name is Ming-Chang Liu, and today I'm just gonna tell you a little bit about how SIMS has advanced our understanding of the solar system formation. Just a little bit about myself. So I graduated in 2008 from UCLA under supervision of Kevin McKeegan, and then I did a couple postdoc appointments at Carnegie and CRPG, working with Larry Niffler and Mark Sosidon, respectively. Then I went around the globe and at the various locations. Then I just arrived at Lawrence Livermore National Laboratory about 2.5 years ago. And I've been involved with a couple of sample return missions, namely Stardust and Hayabusa 2 analyses. I'm interested in using meteorites to understand how solar system form and understanding the fundamentals and develop applications of secondary ion mass spectrometry to understand the solar system formation processes through meteorite analysis. Okay. Okay, so basically, so this slide includes all the samples that I have analyzed. I'm studying. I've studied in the last 20 years, and so today I'm just gonna focus on the left part of the slide. Basically, I just wanted to talk to you about how analyzing meteorites and asteroid samples in SIMS laboratories would help us understand the formation process in the solar system. So from a theoretical standpoint, the solar system formation has been kind of at least I would say reasonably well understood. So we know that our sun started out being a dense core in a giant molecular cloud, and this core would undergo gravitational collapse. So materials in this envelope would fall towards the center, making it hotter and denser. Once the temperature is high enough to ignite a nuclear fusion, to burn hydrogen into helium, then we have a young sun. And at that time, at the really early stage of this star formation process, there was, this envelope is still thick, materials still keep falling towards the center, and the star has to keep the angular momentum conserved. So it has to continuously throw stuff away. That is manifested by this bipolar outflows. Then sometime later, the stuff in the envelope already dissipated, either accreted to the sun or went out to the interstellar medium. Then we have a disk full of gas and solids. Then sometime later, once the gas and solids dissipated, it became the solar system we see now. So it's a very simple. I mean, from the theoretical point, this is a very generic view of how the sun made a form. However, we cannot really go back in time 4.5 billion years ago to witness the formation of solar system. So astronomers have to use telescopes to look at distant young stellar systems to infer and use the information to infer what the solar system formation condition may have been like. And there are several fundamental questions associated with the solar system formation process. One is whether the sun was formed in isolation or the sun formed with a bunch of siblings in a giant molecular cloud. So if a sun formed in isolation, then it's just it's a lonely, it does not have any big siblings to form with. But if it form in the giant molecular cloud core, you see that there are a bunch of young stellar systems that might have formed together with the sun. So that's question number one. The second question is, the second question has to do with the processes happening in the solar protoplanetary disk. So this is a very famous image of a young stellar system taken by the ALMA Observatory. This is HL tau, and you can see those concentric ring structure, which is interpreted as a result of planet formation. Okay. Then if you zoom in onto the center part, to the star, you can see that there are a bunch of gas clumps, and astronomers interpret those clumps as a result of, well, basically they interpret this as a result of ongoing planet formation process. So we don't really form this Earth-sized planets directly out of gas. There are several steps involved before you reach Earth-sized planets. The first step being you have to condense dust and basically teeny tiny dust particles out of gas. And those dust particles would, accumulate to form bigger and bigger objects, and eventually it reaches the size of terrestrial planets. So one question that I have been very intrigued by is, what is the time scale for the first step? In other words, what is the time scale for dust condensation? And now there's also another interesting phenomena that's been observed by the Chandra X-ray space telescope, which is the enhanced X-ray luminosity seen from those young stellar systems. And astronomers interpret this as a result of enhanced emission of energetic charged particles. So did our sun also go through this phase? If it did it leave any trace of charged particle spallation in the early solar system objects? So to address the questions I just described, I resort to the so-called short-lived radionuclides. In this context, the short-lived is the short-lived radionuclides are the radioactivities with half-lives of order 10 million years or less. But if you ask people from different disciplines, they will have different answers or definition regarding short-lived. For example, if you ask nuclear physicists, they will tell you the short-lived is really, half-life of millisecond or so, because they are interested in really fast decay. But for us, 10 million years or so is a right time scale, because this time scale is very short compared to the age of the solar system. So even though those radionuclides were present in the beginning, they are essentially extinct now. But the half-life, but the lifetime is also long enough for them to stick around for some time before they get incorporated into early solar systems objects. So the working principle of using short-lived radionuclides to address those questions is that if two or more of those radioactivities originated from the same source and then were co-delivered into either the parental molecular cloud from which the sun formed, or into the already formed disk, and then got incorporated into early solar system solids in a self-consistent manner, you can imagine that those radioactivities will exhibit a concordant decay behavior in terms of their abundances. But there's also possible. So if we can understand the origin and the abundances and distributions of those radioactivities, you can back out what their origins may have been, and from there you can also infer the formation environment of the solar system. So, for example, those radioactivities could have been delivered from stellar sources, and then but they could also be delivered. They could also be produced in situ in the solar nebula by charged particle spallation emitted by the young sun. All right, so so if we can understand the correlations of those radionuclides in early solar system, then we can have a better constraint on the processes that we talk about. There's also possibilities that those radionuclides could have been inherited from the background interstellar medium. So this is more like a classical view of the origin of short-lived radionuclides. And starting about 15 years ago, the models for origin of short-lived nuclides have been slowly moving towards a generic view. In other words, you don't really need a specific source for those radioactivities. Rather, having those radioactivities is just a natural process of star formation. So the sun could be the second or third generation of stars in this giant molecular cloud. And when the sun formed, the molecular cloud was already enriched in a bunch of short-lived radionuclides due to the contribution from the earlier generations of stars. Okay, so so this is basically just a natural consequence of star formation. You don't really need any specific source to get those radionuclides from. Okay, so how do we, how do we analyze? So in what sample do we analyze those radionuclides? Well, thank God there are leftover building blocks of terrestrial planets, which reside now in the so-called asteroid belt. So these are, asteroids, and if part of the asteroid gets, broken off and fell toward the Earth, then we see a big shooting stars. And if they land, they could land in a desert or in Antarctica, then or even in your backyard, then meteorite hunters will go look for them, and also scientists will go look for them and collect them, bring back to the laboratory for studies. Or they could hit your car and make you kind of rich. But now these days, instead of waiting for the meteorites to come towards us, we can also go to them to collect the samples. The beauty of those sample return missions, the most recent two being Hayabusa 2 and OSIRIS-REx. And the beauty of the sample return mission is that we know from which asteroid we collect the sample. For meteorites, we can only infer, we can only backtrack what the orbit, but we don't know exactly from which asteroid those meteorites come from. Okay. Okay, so a type of meteorite is called chondrite. Chondrite is basically, I would call it, a cosmic garbage can or cosmic sedimentary rocks. It contains, high temperature components as well as low temperature components. Today, I am going to focus on just one specific type of high temperature component, which is called calcium aluminum rich inclusions. Its size ranges from probably, around 30 to 15 micron, all the way up to a centimeter or two. And these are the oldest datable solids in the solar system with the absolute radiometric age of 4.567 billion years old. And this age is taken to represent the age of the solar system. So there are also other high temperature components like igneous rocks, if you will. They call chondrules. These are round-shaped objects, and they form. They have been told they have molten or partially molten. They form in the nebula, And the reason chondrites are called chondrites is that they contain chondrules. And there are also the olivine aggregates, which are fine-grained olivine, aggregates, which it represent, early solar system condensates. But as I said, chondrites are cosmic garbage cans. Some chondrites have undergone aqueous alteration. So in some chondrites, you can see secondary mineralogy, like due to the aqueous alteration, so such as carbonates and magnetites. Okay. But again, today I'm just going to solely focus on calcium aluminum-rich inclusions. All right, so astronomers use telescopes to look at distant stellar objects. And my telescope is secondary ion mass spectrometers. This is a picture of the UCLA IMS 1290 ion probe, which is the ion probe I use for the longest. This is, I would say, a pretty advanced ion microprobe. It's got advanced ion source, oxygen ion source named Hyperion, which would allow it to have high spatial resolution. You can focus the beam down to a couple microns for spot analysis, but you can also focus the beam down to like submicron if you want to do ion imaging or high resolution ion imaging. And this is a big instrument, has a big magnet, so it features high transmission. As a result, we have enhanced secondary ion signals. And from the enhanced secondary ion signals, we will be able to get high precision analysis done. Sometimes, is for certain elements, and the precision sometimes can be as high as 0.1%. Sorry, 0.01%. Okay, I think this is probably a good place for a quiz, Celine.
Okay, 5 more seconds. Very good. And here are the results. So Ming-Chang, can you confirm the answer?
Yeah, the asteroids is the correct answer. Of course, chondrules are still, chondrules, you can say they are leftover bits from the solar nebula. And some chondrules actually, some chondrules are in the asteroids or in the carbonaceous chondrite, but the asteroids is the correct answer. Chondrule is just a subcomponent because not all the asteroids that contain chondrules end up being in the terrestrial planets.
Thank you. And
right.
now I let you continue.
All right, thank you. All right, so wait, hold on. Okay, now before I go into some technical details, I just want to introduce you a concept called isochrons. So especially isochrons for short-lived radionuclides. Because now the short-lived radionuclides are extinct, so we don't really get the abundance of we don't really get time information out of short-lived radionuclide isochrons. Let me tell you why. So I'm using aluminum-26 as an example. Aluminum-26 decays to magnesium-26 with a half-life of 0.7 million years, give or take. So the amount of magnesium-26 you see today in your lab, in the laboratory, equals to the amount of magnesium-26 that your sample formed with, plus the radiogenic magnesium-26, all right? Then you can replace this radiogenic magnesium-26 with the initial amount of the amount of aluminum-26 that sample incorporated. So so we use aluminum-26 0 to represent the initial abundance. Okay, but the mass spectrometers do not like to measure the absolute abundance of any isotopes. It likes to measure isotope ratios. So we normalize magnesium 26 to magnesium 24, which is the most abundant magnesium isotope. And then do a little bit of rearrangement. We end up getting 26 over 24 ratio, which is the ratio you measure in the lab today, equals to the initial magnesium 26-24 ratio your sample formed with, plus the alumagnesium ratio of the sample, which is also a quantity you can measure in your lab, divided times 20 aluminum 26-27 ratio. Okay, because aluminum 26 is no longer with us, so we have to use this stable counterpart, which is aluminum 27. So now if we plot aluminum magnesium in the x-axis and the magnesium 26-24 ratio in the y-axis, then the slope will give you the inferred initial 26-27 ratio. I will tell you how this works in the following animation. So imagine you have 3 samples or 3 components from one sample that form at the same time in the same reservoir. And due to chemical affinity, those samples have different alumagnesium ratio. All right. So, and then it also it incorporates aluminum 27 as well as aluminum 26. So this sample form at time 0, at T0, sorry. Then we just let aluminum 26 decay, and then you measure the sample yesterday in your lab, and you will find that magnesium 26 axis is positively correlating with the alumagnesium ratio. Okay, and the slope of this regression line gives you the gives you the aluminum 26-27 ratio at time 0. Okay, now, so that's basically what this quantity is. But now imagine there's a second object that came along in the same reservoir sometime later at T1. So because part of aluminum 26 had decayed, this amount of aluminum 26 decay would elevate the bulk magnesium 26-24 ratio in the reservoir. So the second object would have a slightly higher 26-24 ratio to begin with. All right, and then so the second object also incorporated aluminum 26, but at a lower amount. Then you let aluminum 26 decay. Then you end up getting a second line that has a shallower slope. All right. Then what you can do is you can figure out the time difference between T0 and T1 using the differences in aluminum 26-27 ratio between the 2 objects. So what this tells you is that the short-lived radionuclide isochrons do not give you absolute time, but rather they give you a time difference between objects. In other words, I cannot tell you, if this sample was formed in 1900. I can only tell you that the 2 samples may be 10 years apart, but I cannot tell you exactly when those 2 samples form without any other absolute chronometers. Okay, so now let's talk about if we have an extreme case, that is the third object forming in the same reservoir after aluminum 26 had completely decayed away. Then this sample would incorporate no aluminum 26, and hence therefore you will not see any magnesium 26 axes. You are seeing a flat line. But this ratio, the elevation in 26-24 ratio just due to the complete decay of aluminum 26. Okay. And then this is just, and then now I'm just gonna tell you something a little more complicated. Now, as again, we have something that form in T0. Then at T1, which is not too far, that's still when aluminum 26 was still alive, but after T0, this sample had been, the magnesium isotopic composition in this sample had been completely homogenized. Therefore, you will have then you will basically reset the clock. Then at time zero, this magnesium quickly after the isotopic resetting, the system arrived at isotopic closure. In other words, no magnesium coming out or in, no aluminum coming out or in. Then you let aluminum-26 continue, then starts decaying again. Then you analyze the sample, in your lab, and you are getting a slope that indicates the aluminum-26-27 ratio at T1, not at T0. All right, even though it formed at T0, but the isotopic, the thermal resetting would result in a slope that does not reflect time at T0, but rather at T1. Okay, so that's how the chronology would work. But the initial abundances of those radioactivities also provide you with important information about their astrophysical sources. So I will tell you why that's the case later. So now I'm going to just introduce you a so-called delta notation. Basically, this is the parts per thousand deviation of the measured isotope ratio from the reference value. Okay, and you see this very often in cosmochemistry literature. Okay, so I think now this is a good time for the second quiz, Celine.
It looks like everyone has answered. Almost everyone. 5 more seconds. Very good. You've been paying attention. Yes.
All right. So, right. 2 asteroids. Yes. So it's Hayabusa 2 and OSIRIS-REx. And Chang'e 5, that was the sample return mission to the moon, not to an asteroid. And Hayabusa 1 and Hayabusa 1 came back in 2011. So it's some time ago. All right.
Thank you.
All right, thank you. And then now let's get into the first topic, timing and timescale for dust condensation and coagulation. And to address this question, we are using aluminum-26. Oops, sorry. Okay, so now aluminum-26 is probably I would say the most extensively studied short-lived radionuclide in the solar system. And the initial ratio of 26-27 ratio of 5.2 × -5 was well established almost 50 years ago by my undergrad advisor, Typhon Lee. And this value has been determined for many large centimeter-sized CAIs, calcium aluminum-rich inclusion, from a particular group of carbonaceous chondrites called CV chondrites by both in situ and bulk sample measurements. So these two slides show the CAIs analyzed using the bulk method, and CAIs analyzed with the in situ method. So for bulk samples, you basically dissolve one CAI and then analyze this magnesium isotope. So one data point here represents one CAI. So you can see that there are 5-6 CAIs falling on this isochrone, and the slope gives you the aluminum-26-27 ratio of 5.2 × -5. And this number is also found in this very nice study using the in situ method. So this McPherson analyzed this fine grain CI, which is a CI that has never been melted, and it's representative of initial nebular condensates. So it's supposed to be very pristine. And then he analyzed multiple components within this inclusion, and he also ended up getting 26-27 ratio of 5.2 × -5. All right. So this tells you that the aluminum-26 was homogeneously distributed in the CAI forming region. And using this time, using the errors you get from the initial 26 to 27 ratio, people infer that the large CAIs probably formed within a very short time scale, which is plus minus 20,000 years of 5.2 times minus 5. Okay, this is just inferred from the analytical error of this ratio. All right. Okay, so from my view, I would say that 5.2 times minus 5, since it's found in a lot of centimeter-sized objects, I would say 5.2 probably represents the time point for the formation of centimeter-sized objects. All right, there are values lower than this in the CIs that have undergone melting and recrystallization. So that reflects isotope resetting at a later time scale. But I'm more interested in knowing what the aluminum 26-27 ratio may be when the dust particles were still condensing from the nebular gas. So we have already had a little bit of idea about this. We have analyses of corundum grain, which is just pure aluminum oxide, and the hibonite grains, which are just calcium aluminum rich oxides from various chondrites. But one thing you notice is that those samples are fairly small. So this is like a couple micron corundum inclusions, and these hibonite inclusions are probably the 30, 40 microns in the longest dimension. All right. So in the past, we because of before the Hyperion source came along, in order to get high precision, we really have to use a big spot size, and the spot size is about the same size as inclusion. So basically, you are getting you're doing a bulk equivalent of bulk analysis of these teeny tiny dust particles. And then we infer the aluminum 26-27 ratio using a model isochron. In other words, you have you generate one data point from the bulk and from this inclusion, and you connect this point to the origin of and then infer the slope and calculate this and infer the aluminum 26-27 ratio from the slope. So that's what's called model isochron. So using the model isochron, people have found that the corundums in the aluminum 26-27 ratio in corundum is bimodally distributed, with the most with one peak falling at 0, in other words, no aluminum 26, and the other peak falling on roughly 4.5 to 10⁻⁵ with a really big error, all right, or really large spread. Similar observation was also made in those hibonite grains. There are two populations of hibonites. One population carries no radiogenic magnesium 26 excesses, but rather magnesium heterogeneity that is independent of the aluminum to magnesium ratio. The other groups showed a multimodal distribution of aluminum 26, with the most dominant one being at 4.9 10⁻⁵. But what's interesting is, so that's basically consistent, within error with the study found in the corundum inclusion. But this also allows for a possibility that there might be something at the higher value at 6 10⁻⁵. Okay, so we don't know at that time. We couldn't do any better. But so we could only do model isochron, but we don't know if that's connecting the data point to the origin is a valid assumption or not. All right, and in addition, CM chondrites have undergone a certain degree of aqueous alteration. So what would water do to the magnesium isotope at that time was not clear either. So with the Hyperion source, I was able to, for the work that I'm going to describe later, I focus on a study of one of the most primitive carbonaceous chondrite called LLNL 77307. This was collected in Antarctica. It belongs to the CO group, all right? And it contains CAIs of different morphologies, of different mineral compositions. But one thing that's in common is that they are all very small. So they are probably no bigger than 50 microns in the longest dimension. And well, thanks to Hyperion source, I was able to look at the magnesium isotopic composition of the individual mineral components to construct a internal isochron for each inclusion. So in the next few slides, I'm gonna show you some isochron results. So this is just one sample, and again, this is a 30 micron inclusion. Oh, what happened? Sorry. This is a 30 micron inclusion, and I am able to place 5 spots on the sample and get an internal isochron with the slope corresponding to 26-27 ratio of 5.4 times 10 to the minus 5. And the reduced chi-square, which is the goodness of fit, indicates that this is a valid isochron. The second sample is characterized by a slightly lower 26-27 ratio. Again, 30 micron inclusions. I placed 3 spots each, and this is a nice isochron with the reduced chi-square 1.0. So again, this is a valid isochron. The sample was not disturbed after this time, after aluminum 26-27 ratio was after aluminum 26 was was last incorporated at this abundance. And the third sample yields a even lower 26-27 ratio of 2.4 times to the minus 5. The fourth sample basically has a slope corresponding to 26-27 ratio not resolved from 0. Okay, so this means that this sample was completely reset by whatever process. But not every isochron is a well-behaved isochron. So for example, in this inclusion, that's a 10 micron inclusion, and you can see that the this aluminum 26-27 ratio has, even though it's sure it's lower, but its reduced chi-square is 22. So that means this magnesium isotope system is largely has been significantly disturbed. All right, so I analyzed probably 1920 inclusions from this carbonaceous chondrite, and then I was able to compile a histogram as well as the probability density plot from the data, and so that's shown by this white curve. Then I also plot the literature data from my earlier study and from a study at the University of Chicago using the 1280 instrument at University of Wisconsin. So the literature data is shown as the gray curve. So what literature data shows is that there was a dominant peak at a dominant mode at 4.9 times to the minus 5. And this mode is reproduced by the new data. Okay. But what's interesting, from the new data is that we also see a peak at slightly higher value of 5.4, and this peak is resolved from this 4.9 times to the minus 5 peak. So I wanted to know what's what this peak is really about. Then I make a isochrons from multiple CAI isochron. I used all the data points from those 5 inclusions and make an isochron diagram. And I found that the inferred 26-27 ratio is 5.4 times, plus minus 0.1 times the minus 5, and the reduced chi-square indicates that these, data points belong to the single population. So my take on this is that 26-27 ratio of 5.4 marks the formation of inclusions, it's really small inclusion by accretion of micron-sized dust particles. And if we play the same game using the errors on the isochrone, we can infer that the condensation timescale is of order 50,000 years. Then when we look at the second peak, then sure enough, we are getting a 26-27 ratio at 4.9 times the minus 5. And there's a larger scatter indicating that maybe there has been some disturbance happening to some of the inclusions. And so my take on this is 4.9 times the minus 5. There was a major thermal event in the nebula, roughly around 100,000 years after initial condensation. And, similar to previous studies, we have also found inclusions without aluminum-26. And this time, again, I'm using, instead of having a big spot that covers the whole inclusion, I was able to put multiple spots on individual inclusion and found that the magnesium-26 its magnesium isotopic composition was indeed independent of the aluminum-magnesium ratio. Most of them shows no excesses, radiogenic excesses. So to me, this indicates the initial magnesium isotope heterogeneity. So let's go back to this dust condensation timescale. So from the data, my take is that the condensation time for the micron-sized dust in the nebula is characterized by the magnesium heterogeneity as well as homogeneity of aluminum-26. All right, that sounds very strange in the beginning, but how can you have such a contrasting isotope distributions at that time? Well, it's, if you think about it, it's not that crazy because as I said, the dust condensation probably happened within a 50,000 year time scale. And we have zero resolution into what happened within this 50,000 years. So basically, this is the dark age that we have no resolution into. All right. So it could be that the initial heterogeneity was homogenized within such a short time scale. All right, so then from the dust condensation to agglomeration into millimeter to centimeter size objects, this is about 40,000 year time scale. So let's go back to the astrophysical environment. How can we use the aluminum-26 data to infer what the astrophysical environment of a solar system formation may have been? Well, we know that this, homogenization, aluminum-26 homogenization timescale is less than 50,000 years. So that means there was already presence of this radionuclide in the molecular cloud core. Otherwise, it might have taken longer to reach homogenization. So this means that you either have to inject aluminum-26 into the molecular cloud core from which the solar system formed, or you inherit aluminum-26 from the enriched molecular cloud core. So this means that the sun was probably formed together with other siblings rather than formed in isolation. And then now let's talk about the charged particle part. For this part, we have to use beryllium-10 because beryllium-10 is a radionuclide that exclusively requires a spallation origin. All right, it doesn't get produced by any stellar nucleosynthesis process. But there are two possibilities. There are two locations where you can form this radionuclide. One is you form this radionuclide in situ in the protoplanetary disk, or you can form this radionuclide in a molecular cloud core, and then this radionuclide gets incorporated, into the interstellar medium, and then this radionuclide gets incorporated into the solar system parental molecular cloud core. So we have to figure. So if beryllium-10 is coming from the outside, then it's probably very homogeneously distributed in the molecular cloud. But if it's produced locally, then you can imagine some sort of gradient, abundance gradient as a function of the distance to the sun. So we have to figure out which one is which. The fossil record of beryllium-10 was first discovered by McKeegan and Chalcedon and Francois Robert in 2000. In this discovery paper, they found that boron-10 axis was in correlation with beryllium to boron ratio. Again, this is the isochron diagram, and the slope of this correlation line gives you a beryllium 10 to 9 ratio of roughly 9 × 10⁻⁴. So this ratio was confirmed by a later study of Chalcedon in 2006. So since the initial discovery, there have been a lot of studies done in the last 20 years. And Emily Dunham, who is currently a postdoc at Lawrence Livermore National Laboratory, published a really nice paper. She used the 1290 ion probe at UCLA working with me and analyzed a lot of CAIs from different carbonaceous chondrite groups. And she organized this inferred beryllium 10 to 9 ratio as a function of chondrite types, as well as special refraction inclusion, special and rare refraction inclusion. And what she found is that the majority of the CAIs from the carbonaceous chondrite, if you don't count those, co-fun or F inclusion, just remember those are special inclusions, special and rare inclusions. If you exclude those special and rare inclusions, the majority of the CAIs are characterized by a beryllium 10 to 9 ratio roughly at 7 or so ×⁻⁴, which basically is consistent with the study by Chalcedon and McKeegan and collaborators. All right. So, but if you remember from what I just talked about earlier, aluminum-26 was homogeneously distributed in the solar system. So if beryllium-10 was also homogeneously distributed in the early solar system, given their chemical affinity, in other words, they like to go into high temperature solids, one can anticipate that those two radionuclides would decay in a consistent manner. In other words, there will be a co-decay. Their abundances will follow. The abundances in CIs will follow this co-decay curve. Okay, so this is the beryllium 10 to 9 ratio plotted against aluminum 26-27 ratio. This is an old plot, but the fundamental idea remains. You can see that there's in the normal CAIs, there's a range of beryllium 10 to 9 ratio, but it does not really follow the aluminum 26-27 ratio. It doesn't really follow this co-decay curve, all right? And then some special inclusions, those rare and special inclusions also do not follow this co-decay behavior. So in this study, I just wanted to analyze more those rare and special inclusions. They have been determined for their aluminum-26 abundances. One inclusion is called Shao, has essentially no magnesium-26 excesses. We can only infer an upper limit for the 26-27 ratio, being 3 × 10⁻⁶. The other one is called Hidalgo, which is something I just published at the end of last year, has a well-determined 26-27 ratio of 1.5 × 10⁻⁵. So and then I analyzed its beryllium-10 to 9 ratio in those inclusions. And we found that those two inclusions are characterized by contrasting initial beryllium-10 to 9 ratio. Shao has the 10 to 9 ratio of roughly 3.5 × 10⁻⁴, and then Hidalgo has a 10 to 9 ratio of 7.5 × 10⁻⁴, which is consistent with what you see in those normal CAIs. So now if we plot them back to this plot, and what we see is that, again, they do not really follow this concordant decay curve, okay? So to me, this is an indication that beryllium-10 was heterogeneously distributed in the early solar system. Therefore, my take on this is that, yes, we do see traces of charged particle spallation in the context of beryllium-10 abundance. So now let's make a conclusion. So for the dust condensation timescale, I think from the aluminum-26 records, we can say that we infer that the dust formed within 50,000 years of solar system, which is a really short timescale compared to 4.567 billion years old for the solar system age. And then the sun formed in a cluster. And yes, the sun probably went through this intense charged particle emission phase in the early solar system because we saw this heterogeneous distribution of beryllium-10. So that's all I have, and I welcome any questions.
We have last final quiz. How old is the solar system? And done. So let's see the result. Very good. I think almost everyone got the right answer. 4.567 billion years.
All right, thank you. Yeah,
okay.
This number is very easy to remember. It's 4, 5, 6,
Yes.
7.
Yes. Thank you again, Ming-Chang, for this nice presentation.